just to correct the notes. So if we have if we want to consider the conjugate function f star of y, right? This is equal to, by definition, the max over x, y transpose x minus f of x. And now here we're going to consider the max over x, y transpose x minus lambda f of x. This is just equal to lambda times the max x, 1 over lambda y transpose x minus f of x is equal to lambda times f star 1 over lambda y, modulo running out of space on my sheet. Sorry. So that's the property that we used. Okay. Anyways, let's continue. So now we have a regressor matrix, and we'll see that this actually complicates the situation a significant amount, because now the nice structure that we had in the Hessian, namely the graph Laplacian, is no longer applicable due to this regressor matrix, which in general we're going to assume we have just some dense matrix X. Let's see why that is. So now, first of all, if we write down the dual problem is a fair bit more complicated, because in order to form this dual, what we do is we introduce an auxiliary variable z equal to d beta. We also introduce an auxiliary variable, let's call it y equal to x beta. And so now we have two equality constraints, y equal to x beta, z equal to d beta. And when I write that down, for those two equality constraints, I'm going to have two dual variables, v and u. And in addition, I'm going to have this linear condition coupling the v and u variables. And so I'm not going to write down the whole derivation. It follows basically the same steps we did before, except we have one more term. And so again, we can consider how do we recover the beta variables from the dual variables. And we have to solve this system. And so now we have to solve a linear system in X. And I actually wouldn't necessarily agree with this slide that it's very expensive. I mean, generally, if you have a covariate matrix X and you want to solve a problem using X, solving a linear system is not totally unreasonable. But anyways, it's a lot more expensive than it was before due to the X variable, or due to the X covariate matrix, the regressor matrix. And all right. So now, using this new dual problem, let's consider what our dual proximal gradient descent method is. And so now the constraints are significantly more complicated. If you remember in the first time we went through this exercise, we just had a simple u restricted to the infinity ball, L infinity ball. And so now we have two variables. These two variables have a particular relation, namely x transpose u plus d transpose v equal to 0. And so in order to solve for this prox operator, significantly more complicated, and in fact requires an intersection of basically the plane that corresponds to the linear constraint and the box for u. Okay, and similarly, the dual interior point methods are more complicated, because we have this linear constraint which ruins the structure due to having the x variable. So instead of having a nice sparse, really the one way to think about it is the system that we had to solve for the Newton step in the previous example. We had a Hessian that had a very nice sparse structure that we could exploit. That sparse structure is no longer there, because now we have this dense X matrix, which is in the Hessian. So no longer are we going to be able to derive a dual interior point method that has order n flops. Of course, we can still do the subgradient method, but we prefer not to. All right, so now we're actually going to revisit one of the methods that we ruled out in the original problem and argue that it's actually a reasonable approach for this scenario. in particular, for the case where we don't have the regressor matrix, we ruled out the proximal gradient applied to the primal problem. And the reason was that's because it involved the prox operator, which was roughly the same difficulty as the problem itself. But in this case, the nice property of the prox operator is that the prox operator does not involve the regressor matrix. And so this prox operator is still a little bit difficult to compute. But in fact, we just developed a fast method for computing this prox operator. And namely, the prox operator is just the diffuse lasso problem without the regressor matrix. So now we can use this fast method that we derived, the dual interior point method, namely, to solve for this prox operator, and use this prox operator in the inner loop for a proximal gradient descent method. And so, so the nice thing is that we've kind of decoupled the computation of the prox operator from the dense X matrix. And so yeah, so the same caveats still apply. So in order to do this, we have to compute the gradient, which is shown here. And so the nice part is that we don't require solving, in order to compute the gradient, it doesn't require anything like solving a linear system in X. We just need to be able to multiply by X and X transpose. And so the same caveats that we applied before to the gradient descent method are still relevant here. It may take many iterations to converge, but given the complexity of interior point methods for this problem, this seems like the right trade-off in practice. All right, so now we're going to talk about a even more special case of the diffuse lasso. So in general, what I've said so far is for a diffuse lasso applied to a general graph. And in that case, we get an interior point method by using the graph Laplacian and solving for the Noon direction. It turns out that, in fact, if we take just a simple case of the 1D diffuse lasso, then there is an even faster method that can be used to compute the prox operator based on dynamic programming. And so this is a really cool method. It's actually fairly a little bit involved to derive. It's kind of it's a little bit unique, I would say, in convex optimization, in the sense that usually I guess what I would say is not immediately obvious that the algorithm is not immediately obvious. And so it doesn't involve any kind of linear algebra, really. It really involves kind of, well, this is way too much detail, but it really involves looking at the diffuse lasso problem as kind of looking at it as a hidden Markov model where the parameter beta is your hidden state, and you do a forward-backward pass to compute beta. So it's a nice approach. It's quite involved for what seems like a fairly simple problem. So in practice, how fast is this dynamic programming method? And so it turns out that we could instead we compare here on the graph that what's required to solve the prox operator for the 1D diffuse lasso case versus just solving a banded matrix that is essentially the banded matrix that's required for solving for doing the graph Laplacian solve for the graph Laplacian solve for the chain graph. And so in order to these two operations aren't actually comparable because you need to do many banded matrix solves to actually, if you're going to use this method to compute the prox operator. But even one banded matrix solve is more expensive, at least in this particular implementation, than the dynamic programming algorithm. So we have a really fast algorithm for computing the prox operator in this special case where the graph is a chain graph.
What is the banded matrix solve?
So if you take the D transpose D, DD transpose matrix that appears in the Hessian that we saw before, that's actually a tridiagonal matrix. And so you can compute the inverse. You can solve a linear system that's what's called a banded matrix. And so you can compute the linear system basically with an order n pass over over the rows of that matrix. Yeah. Sorry? So yeah, so it's really, so it's a good question. Actually, when I looked at this graph, I expected the order of the curves to be reversed because, yeah. So I don't know that the absolute difference between those two curves is really too relevant because it's really constant factors of the implementation that makes a difference. But what is relevant is that the Band-Aid matrix solve is you have to repeat that, say 10 times, for example, in order to actually get convergence, for the Newton method, where you only have to compute this once. The dynamic programming approach gives you the solution after just one of these operations. So it's really the right comparison in terms of computing the same function is 10 times or so the red line versus 1 time of the blue line. So the absolute difference, I think, is a little bit more of an implementation detail in the way that Ryan actually created this graph in R. All right, so let's look at an example of where we use the diffuse lasso. And so this is an interesting example. I think this is actually Ryan's group that produced this example. And so here we have a set of covariates. And again, we're trying to produce, this is somewhat similar to the MRI example because we have a set of subjects. And we want to, I guess it's the second one's a little bit morbid. We want to predict whether people die or not. And in order to predict these outcomes, what we do is we have a bunch of input features corresponding to, so for example, this one, DigCore, is basically corresponding to how well a person can, is corresponding to how well a person can actually recognize handwritten digits. And so based on these various factors, we're going to construct a model that predicts what's going to happen to them down the line. And so we expect such a model to have this kind of constant structure in time. Like we don't, if you didn't impose this particular penalty, the diffuse lasso penalty, over these covariates, then you would see this would be a lot more, there'd be a lot more noisy as the weights jump. But like if this is a factor that's actually predictive of what happens, we expect the weight to be roughly the same at age 65 versus age 66. And so by constructing the model such that we regularize these coefficients to be piecewise constant across time, we get this nice structure that statistically makes sense. All right, so now we're going to look at the kind of what's the trade-off between what happens versus the proximal gradient method versus the Newton method and how many iterations it takes to converge. And so on the left-hand side, we have is basically showing that for certain methods there's a dependence on the parameters, and so that essentially on the left-hand side, for large lambda, we have a highly sparse solution vector, and so we have that it takes a very few number of iterations to actually converge to the solution. In the simplest case, the lambda, the solution vector is just 0, so it takes no iterations, or it takes 1 iteration, and so versus the interior point method takes roughly the same number of iterations, although there's a little bit of, yeah. So essentially, there's a trade-off here where if you compare these two curves, since these are both similar complexity, then as we've argued, the proximal operator and the number of, and each Newton step costs the same amount of iterations. And so essentially, there's a trade-off on this curve where you get to a point where it makes a lot more sense to use the Prox method versus the Newton method. And so, as we kind of argued before, one of the reasons for this is that if we have a large lambda, then we have few active parameters in the primal problem, and so that's going to be we have a sparse solution. So there's kind of less free variables to optimize. But if we have a small lambda, then we have fewer active variables in the dual solution. So it goes back to what I was describing with kind of the dual relationship between the primal variables and the dual variables and the sparsity that's there. And so essentially the intuition here, and I would add the caveat to this intuition that it also depends on what the actual optimization algorithm is. But the intuition is for these kinds of problems that we have a large lambda, that's going to be easier for the primal algorithms versus the small lambda is going to be perhaps easier for dual algorithms. All right. Let's see. I think I'm going to. All right. So I think I'm going to leave it there and let Ryan take off talking about other kinds of differencing operators rather than just the graph fuse lasso operators. Then we'll also talk about group lasso problems, which also fit into this framework next time. All right. Thanks.